Hello everyone, in this video we're going to be looking at the core practical for measuring the density of both regular objects and irregular objects. So if you're ready, let's get right into it. Now let's have a look at regular objects method for determining density. What I mean by a regular object is really an object that has regular lines. So things like cubes, close enough, things like rectangles, all sorts of objects which have regular straight lines that you can measure quite easily, right? You don't want anything with curves. For anything with curves, that's an irregular object, and we're going to look later on in the video how we can work out the density of those. But the regular object method is really easy, and honestly it's just a bit of common sense. So if you ever do forget it, just think, what would I do to actually get the density? So let's start off with the actual method itself. So number one, weigh the mass of the object using a zeroed weighing scale. A zeroed weighing scale really means that you've checked that the initial balance on the actual scale is at zero, right? Because you can get some sort of errors, which would be systematic error if your scale wasn't zeroed at the very beginning. So you want to measure the mass using a zero weighing scale. This will give us the mass in kilograms straight away, okay? Because I have my equation here for density. Rho is equal to m over v, m being the mass, v being volume. So we have our mass straight away. That was easy. Now we want to find out the volume. So what do? We use a 15 centimeter ruler and measure the dimensions of the object. So we're talking about length, width, and height. There you are. Okay, yeah. So LWH, right? So we're measuring all of these dimensions using a 15 centimeter ruler. Why have I said 15 centimeters here? Well, that's because it would be a bit stupid, right, to use a meter ruler for a cube that probably fits in your hand. So you want to have a decent sized 15 centimeter ruler to actually get a sort of accurate reading. We're not going really overboard on it, okay? So that we would use a ruler to measure the dimensions of the object. Now, after we measure the dimensions, those dimensions are going to be in centimeters because, centimeter ruler doesn't even go up to a meter. So we convert those into meters and we multiply all the dimensions together to get the volume in meters cubed. Okay, so that's our volume done. Then to work out the density, all we do is divide the mass by the volume, and then we get the density of our regular object. That's really all there is to the core practical for the regular object's density. Now, can we look at a few sources of errors in this? So let's have a look at errors. So the first error is parallax error. Error in measuring dimensions. So this is when you have to actually do the measuring on the cube itself, right? You have to look at the cube, right? If you close one eye, the reading will look like one thing, and if you close the other eye, the reading will sort of shift. So you really want to make sure that you use that you keep a consistent measure to avoid using parallax error. Because if you start to switch eyes and things like that, you introduce error into your actual the readings. Then there's also zero error. So this is both in the scale, but more commonly because most scales that we use nowadays are digital, so we don't really have to worry too much about zeroing them. This is again in the measuring the dimensions, because again, if your ruler isn't exactly at zero at the corner, you introduce some form of systematic error, right? Error that's present throughout your entire experiment. So those are the two sources of error for the regular method. Okay, so now let's have a look at the method for finding the density of an irregular object. So first of all, again, just like the last object, we work out the mass of the object using a zeroed weighing scale, and that just gives us our mass in kilograms as usual. Now the second bit is working out the volume. Now because this is an irregular shaped object, it doesn't have nice straight lines that we can measure with a ruler. Instead, we have to use something brand new called a Eureka can. Okay, so what really is this? A Eureka can is this thing over here, right? And you can see that it has like a downwards facing spout, and you can see that the water line is just right to where the spout actually starts. So this means that when we place an object into the actual Eureka can itself, the level of the water rises, and because it rises above where the spout is, right, any excess water that's been displaced by the object gets pushed out into this measuring cylinder. So we now know that the volume of water here that's been displaced is equal to the volume of the actual object itself. Because think about this, right? If you were to place an object in water, it can't raise the water level any more than the actual space that it's taking up, right? Because that would mean that it's taking up some sort of invisible space, and that doesn't really work. So the volume of water displaced, is equal to the volume of the object. And again, you're going to be doing this experiment in your school, so don't worry if you don't really understand it right now. As soon as you see it with your own eyes, it really does make really intuitive sense. So the Eureka can was invented by the Greek inventor Archimedes, right? And he came up with this idea when he sat down in his own bathtub and he saw that the level of water rose as he sat down. So we're using that exact same principle here. So number 2 is using a Eureka can and a measuring cylinder, slowly place the irregular object. That is very key, because if you just chuck it in there, some of the water might splash right out the can and it would sort of defeat the whole purpose of getting the volume. So we slowly place the irregular object into the can, and then we read off the measuring cylinder this the volume, sorry, I missed the word there, volume of the displaced liquid. Okay, so then number 3, now we convert the milliliters into meters cubed. I've got M3 here, but you should know by now that this is meters cubed, right? So how do we do that? Well, we divide by a million. Why is that? If we remember that volume is, let me just draw a quick cube. Okay, volume is length times width times height. And because in a cube all of these things are the same, we can really say that volume is, the multiple, volume is really a cube. I can do it like this. Length times by width times by height is equal to a cube, so x cubed, okay? Because if length, width, and height are all going to be the same in a cube, right? So we can just say x. So it's always a cube. So if we have one side which is, because we remember that 1 milliliter is equal to 1 centimeter cubed. To get 100, to get a meter on one side, we have to use 100. And then to get meters on another side, we have to get 100 as well. To get meters on another side, we do 100 times 100 is 100, which is 100 cubed, and that ends up being 1 million centimeters cubed is 1 meter cubed. Okay, I'm sorry if that was a bit all over the place, right? All you need to really understand is that because in one side we can have 100 centimeters, and another side we can have 100 centimeters, and another side we can have 100 centimeters, it's 100 cubed centimeters, right? And that gives us 1 meter cubed. Okay, so we have to divide the milliliters by a million, and that gives us our volume in meters cubed. Okay, so now number 4, all we do is we divide the mass by the volume to get the density of the irregular object as we did the previous one. Now there are also again some sources of errors in here. One source of error is the fact that some water might splash out of the actual Eureka can itself, and that gives you a systematic error because now the error is present throughout the rest of your calculations. Also, we can get some parallax error again in actually reading the measuring cylinder, and we can get again 0 error in the weighing scale.